In this video, I'm going to give you some examples of doing inverse kinematics following the graphical method for some 3 degree of freedom manipulators. The only difference between doing inverse kinematics for 2 degree of freedom manipulators and 3 degree of freedom manipulators is the complexity of the problem. But like many things, practice is the key to getting good at this. So I'm going to show you a couple of examples and give you some tips for how to solve these kinds of problems. And then at the end, I'll ask you to do one on your own and then send your solution as part of the quiz for this section. This first example is the cylindrical manipulator. I've drawn the kinematic diagram here simplified, and I haven't included everything, but there are some things that we need in this diagram and other things that we don't. I'll add in the things we need as we go. We're going to start by drawing this manipulator in the top view. So if we were looking down from the top, we would see the x0 axis and the y0 axis like this. Then we would see the first joint here, and then the second and third joints would be positioned right on top of it. Notice that I'm drawing this in such a way that theta 1 is not 0. It's much easier to solve these problems when your joint variables are not drawn as 0. I need the link lengths in my equations, so I'm going to draw in the link lengths. And then I also need the joint variables, so I'm going to draw those in. I'm not going to draw in the other frames because for the inverse kinematics problem for position, the other frames are irrelevant, so I'm just going to leave them off for simplicity. Now I'm going to draw in the joint variables here. Theta 1 is right there, and then the length of this distance here is actually A3 plus D3. Now I'm labeling the position of the end effector in the base frame. Since the end effector frame is 3, I could represent that as Y03 and X03. Remember that in inverse kinematics, the output of the equation is our joint variables, and the input is the values of the x and y position, x, y, and z position of the end effector. So it's important to draw into your diagram both the input and the output. Have the position of the end effector and the joint variables in the diagram. Now I want to identify whatever triangles I need. Here the only triangle I'm going to use is this right triangle shown in purple here. Since it's a right triangle, I could use Pythagorean theorem or SOHCAHTOA, and I'm going to start by using the tangent. When I use sine, cosine, and tangent relationships are usually the most reliable. So theta 1 can be found just using the input y and x like this. So I have an equation to find theta 1. I still need an equation to find D3 and an equation to find D2. D3 is in my top view equation, so I can probably get it here. Since I've already used a sine, cosine, tangent relationship, now I'm going to use the Pythagorean theorem. So here I have the Pythagorean theorem relationship, and I need to solve this now for the joint variable, since the joint variable is the thing that is my output. So I'll start by square rooting both sides. And then I'll subtract A3 from both sides. Okay, so I have 2 good equations here that have only a joint variable on the left and only known values on the right. I still don't have an equation for D2. and I can't even see D2 in my top view, so now I'm going to draw the side view. Now, when I draw the side view of the manipulator, the only axis I'm going to pay attention to is the z-axis. The reason for this is that I have a rotational joint as my first joint. And so the way that this manipulator might be lined up in the XY plane might be anything. And I don't know how it's lined up in the XY plane. So it's safe to only pay attention to the z-axis when you do the side view. Next, I want to label everything that I know here. Now, since I'm only paying attention to the z-axis, I'm only going to label my vertical distances. A1, A2 plus D2 here. And then this entire distance here is the z position of the end effector. So I'm trying to come up with an equation that says D2 equals something, where the something is all things that I know. So Z03, the z position of the end effector, is A1 plus A2 plus D2, and then I can solve this for D2. And here I have my third equation. So I have 3 joint variables, and I have 3 equations to solve for them. We're good to go. Let's move on to another example. This is the spherical manipulator. In general, the more rotational axes we have, the more difficult it's going to be to do these inverse kinematics equations. So here we're going to move up in difficulty a little bit. We'll start the same way by drawing the top view. I can see my x-axis and my y-axis. And then I'll draw the first joint, and I want to draw this not being in the 0 position. I have a second rotational axis, and then I'll draw the link, there we go, and then the prismatic joint. Next, I want to label everything I know in this picture. Theta 1 is right here. And I want to write in the y and x position of my end effector. Now, here's something very important that I want to point out, because this is a place where people often get confused and fall into a trap. Let's suppose that I want to label the hypotenuse of this triangle, say how long this is, this length that I just drew in green. If we look at our kinematic diagram, it looks at first glance like this length is A2 plus A3 plus D3, but this is actually not true. And here's why. Theta 2 might not be in the 0 position. Let's suppose that theta 2 was at a 45-degree angle. If we were looking down at this manipulator from the top, the distance that it would look like this length here is, it would actually look like it was less than A2 plus A3 plus D3. In fact, imagine that theta 2 was 90 degrees. In that case, this whole part of the arm would be pointing up straight towards us, and the length of this distance would actually be 0. So we do not know the length of the hypotenuse of this triangle right now. For now, we need to leave this unlabeled. Let's just find the things we know. Theta 1 can be written as the inverse tangent of y over x. We can't actually very easily see any other joint variables in this picture. So we'll just stick with this for now and we'll move right on to the side view. From the side view, the only axis we're going to pay attention to is the z-axis. So I have my first revolute joint and my second revolute joint. I want to draw theta 2 as if it's not in the 0 position. There's my z-axis, the only one I'm going to pay attention to in the side view. And then I want to label everything else I know. Theta 2 is right here. This entire length here actually is A2 plus A3 plus D3. Here's the z position of the end effector. Now, I want to identify any triangles that I'm going to use. I've slid the diagram to the left here so we can see it better. I drew a triangle that we want to use in purple, and I'm going to label these two unknown lengths, R1 and R2. Now I can use the Pythagorean theorem to find a relationship that will get me the joint variable D3. And I can solve this now for D3. In this equation, I know the value of A1 and A2, but I don't yet know the values of R1 and R2. So in order to use this equation that we just found, I need to find an expression for R1 and an expression for R2. To get R1, this is pretty simple. I can just use z, the z position, minus the link length A1. I'll call this equation 2. Now, I need to figure out what R2 is. To find R2, we need to actually look back at our top view diagram. We noted previously that this length here is not A2 plus A3 plus D2. This length actually is R2. So I can find an expression for R2 from this top view by using the Pythagorean theorem. And I'm going to call this equation equation 3. So now that I have an expression for R1 and an expression for R2, now I can solve for D3. The numbers that I'm putting on these equations indicate the order that we'll solve them in the code. So each time I label an equation, I have to label it so that by the time we get to that number, we know all of the other variables. Okay, so finally I can find theta 2 from the inverse tangent of R1 over R2, and since I've already solved for R1 and R2, we can do this already, and that's equation number 5. So we now have one equation for each of the joint variables, and we're done with this. We're going to take a look at one more example. This example is even more difficult than the previous one, and it's as difficult as we're going to get in this class. This is the Scara manipulator, and the solving for D3 is actually very easy in this case, but solving for theta 1 and theta 2 is pretty difficult. We're going to start with the top view. There's my first joint. I'll draw it in the not 0 degree position. And now, when I draw my second joint not in the 0 degree position, I have two choices for how to draw it. Here's my X and Y axes. I can either draw the next link over like this, or I can draw it up like this. and then my third joint would be on the end like that. Now, these two configurations each have a specific name in robotics terminology. We call this top one elbow down. We call it that because this joint here is kind of like the elbow. And so in this configuration, the elbow is down, and in this other configuration, the elbow is up. The reason that this is important to note is because you will get different answers for your inverse kinematics equations based upon whether you assume that the manipulator is in the elbow up or elbow down position. In practice, what you want to do is decide whether you want your manipulator to go into the elbow down position or the elbow up position when you give it a target position to move to, and then use those equations that you derived from that diagram to solve for the joint variables. Now, here's what we're going to do right now. I'm going to take the elbow up case and show you how to solve it. Then I'm going to ask you to take the elbow down case, which is similar but a little bit different, and try to solve it yourself. And then I'm going to have you send me your work as a part of your quiz for today. So let's take a look at the solution for the Scara manipulator in the elbow up configuration. I'm going to start by labeling some of the things that I know. This is theta 1, and then this here is actually negative theta 2. The reason this is negative theta 2 is because positive theta 2 is defined here. Since theta 2 has turned in the opposite direction, this actual angle, the value of this angle, is negative theta 2. When you do the elbow down configuration, your theta 2, if you define it like this, will be positive because in the elbow down configuration, theta 2 is turning in the positive direction. All right, let's label some more things that we know. This is the link length A2, and this is the link length A4. I mislabeled these in the drawing. This link length is not A1, it's actually A2 right here, and this link length is actually A4. But I didn't notice that when I was drawing this picture. So just remember that this A1 is actually this link length, A2, and this link length here is actually this link length, A4. Then I have the X and Y positions of the end effector. The end effector is directly below the center of this third joint. Now I need to identify the triangles that I'm going to use in my calculations. I'm going to use this triangle right here, drawn in purple. This is not a right triangle. Then I'm also going to use this triangle right here, which is a right triangle. These two triangles almost always are useful in finding the inverse kinematics equations. The way I picked these two triangles is I used one triangle that is a right triangle where the two legs show me the position of the end effector. Then the purple triangle is the triangle where one of the sides is the same as one of the sides in this right triangle that shows me the position of the end effector. When you do other cases, like the articulated manipulator, which I'm not showing you as an example here, you will also want to pull out these two triangles to use. One triangle that is a right triangle where the two legs show you the XY position of the end effector, or in some cases it might be other axes like XZ or something like that. And the other triangle is one where one of its sides is shared with the first triangle, but the second triangle is not a right triangle. So these are the two triangles we're going to use in this derivation. I'll call the hypotenuse R1. I'm going to zoom in a little bit so we can see the angles a little bit better. Now I'm going to label some of the angles that we're going to need. This purple angle right here, I'm going to call it Phi1. This other angle in the purple triangle, I'll call it Phi2. And then this angle in the orange triangle is going to be called Phi3. So one of the equations that I can use here is that Phi1 plus Phi3 is equal to theta 1. Or another way of saying this is that theta 1 is equal to Phi1 plus Phi3. I could have put the theta 1 on the left. So if I can just find expressions for Phi1 and Phi3, I would be able to solve this equation and have what I need for theta 1. Phi3 is actually the easier one to get from this equation. Phi3 can be gotten from the orange triangle as the inverse tangent of y over x. Okay, now I need an expression for Phi1. Phi1 is a part of the purple triangle, which is not a right triangle. So I want to use either the law of sines or the law of cosines. And almost always the right thing to choose is the law of cosines. Only use the law of sines if the law of cosines ends up not working for you. So since I'm looking for the angle theta 1, I will start my law of cosines equation with the length of the side that is opposite the angle I'm trying to find. So since I'm trying to find Phi1, I'll start with the link length A2. So A2 squared is equal to the sum of the squares of the other two sides, A1 and R1, minus 2 times A1 R1 times the cosine of the angle that I'm looking for, theta 1, or Phi1. Now there's another step we need to do where we solve this for Phi1, but I'm not actually going to do that here right now because that's kind of a trivial step. So I'm going to save some time by just saying that we solve this equation for Phi1. Now I won't be able to solve this equation for Phi1 until I have an expression for R1, because R1 is in this equation. But finding R1 is actually pretty easy. R1 is just the hypotenuse of this orange triangle. So R1 would be the square root of x squared plus y squared. Now as soon as I can, I'll put numbers on these equations to help me remember what order I need to have them in my code. I've already labeled equation 1, so the next thing that we do is equation 2, solve for R1, and then at that point we'll have everything we need to take equation 3 and solve it for Phi1. Okay, so now I've got equation 4, I can solve for theta 1. All I need now is an expression, an equation for theta 2. So here's how we're going to solve for theta 2. I'm first going to recognize that negative theta 2 plus phi 2 is 180 degrees. Can you see why that's true from our triangle here? This is a straight line right here. So if we would go negative theta 2 and then phi 2 more, we would have this entire angle, and since this is a straight line, that would make 180 degrees. So I can solve this for theta 2. Now all I need is an expression for phi 2. Phi2 is one of the angles inside my purple triangle, which is not a right triangle. So once again, I'm going to use the law of cosines. The way that I use the law of cosines is that I start with the length of the link, or the length of the triangle side that is across from the angle I'm looking for. I'm looking for Phi2, so I'll start with R1 squared. That's equal to the other two sides squared minus 2 times the two sides times the cosine of the angle that I'm looking for. I've already solved for R1 previously, so the next step is to solve this equation for Phi2. And once I have the value of Phi2, I can get the value of beta 2. And I'll need to have 6 equations in my code.